Okay, so this part is a very brief introduction to survey sampling. So what is sampling? Well, we in survey sampling we are more mainly care about finite population rather than infinite population. And then sample is a subset of the population. And in sampling, we want to make statistical inference about the finite population without measuring the whole population. And sampling error is the error that results from taking a sample instead of examining the whole population. And why sampling? Well, we want to reduce the cost. So when it comes to measurement, right? When it comes to measurement, measurement means that we say we can interview, right? So we had ask questions. Then there's some labor behind in the measurement. So then the total cost is a linear function of the sample size. So if I have a 1,000 or 10,000 sample size, then it increases with the sample size cost. So then there's a kind of we want to balance, right? Balance between the accuracy. So usually sample size is large increase, then error goes down, but the cost goes up, right? So we want to do some balancing. Also, we want to save time. And sometimes, so for example, if I do, asking questions for the whole population in the United States, it would take a lot of time, right? But if I just use 1,000, phone call, it will be much faster, right? Not just cost effective. Sometimes to get a more accurate information about the population. So that is an interesting part because the main message here is that well-trained interviewer, well-designed sampling with a well-trained interviewer gives a more accurate information than census. Because in the census, you don't have a sampling error, but you have you don't have enough well-trained interviewers. So you may end up having some non-sampling errors, and that non-sampling error dominate can be bigger than sampling error, something like that. So I will get back to this point later again. And also sometimes it is the only way of getting information about the target population. So suppose you are in a factory, right? You want to do test, try a car test, the safety test. You cannot really do the safety test for every car, right? You want to do sampling of the manufactured car so that you can get an estimate. So that is the idea of quality control sampling for quality control. So how to do sampling? Well, we have two types of sampling. One is the property sampling. The other one is non-property sampling. And so this is the main focus. So this is more statistical. But in reality, in commercial survey, non-property sampling is also used, although the statistical background or statistical justification for non-property sampling is somewhat weak. Okay. So roughly speaking, a property rule is assigned to obtain a sample in property sampling. So the key part is that we have some kind of random mechanism based on a probability rule that used to select samples. So we'll see the idea using a toy example. So here's a simple toy example. So this is a very small town. Suppose you have a very small town, maybe smaller than Ames. You have in that town, there's only 4 farms. Okay, so 1, 2, 3, 4. You can label it, and then the size of farm is a kind of in terms of acres, right? 4 acres, 6 acre, 6 acre, 20 acre. So we have 4 farms. The yield, so it could be corn or soybean or whatever agricultural product. So the yield, this guy is very over years, right? Some certain years, in some year, they even though the does not change. Sorry. Although they could, become bigger, but so this is well, this is known before survey. Okay. So you have that information. Before we visit the farm, we already know the size of farms, okay, from some registration or some administration record. So this information is available, but this is not available. This is so the value of y, the yield, is obtained only from the sampled unit. So once we sample, we visit, okay? So visit and ask question, right? Ask. Of course, they have to, their presumption is that if I ask, they will answer. But they may not answer, but that's a different story. So assume that they will respond, right? They will cooperate and honestly answer the questions that we ask. Question is, okay, so in this case, we have 4 farms. So visiting 4 farms is no problem, usually. But suppose, for some reason, instead of observing 4 farms, we want to select a sample of size 2. So we somehow, because of the budget constraint or time constraint, we only have a resource to visit the 2 farms, okay, instead of 4. Now, then it is a very combinatorial problem, right? How many possible ways of selecting 2 out of 4? The answer is 6, right? Nothing, no more, right? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Okay. So if I select 1 and 2, that means we observe. So this is y1, this is y2, this is y3, this is y4, right? So if I select y1, if I select farm 1 and farm 2, that means I can observe y1 and y2 in the sample. So that means I can, so y1 equal to 1, y2 equal to 3. So this guy is actually y1 plus y2 divided by 2, which is 1 plus 3 divided by 2, which is 2. Okay. So that's how we get this number. Other things are same, right? 3 and 4, for example. So this guy is what? 3 and 4. So 20 plus 6 divided by 2, which, oops. Sorry, no. 5 and 15. 5 plus 15 divided by 2, which is 20 divided by 2, which is 10. So that is this one. Okay. By the way, what is the population mean? I mean, right? What is the parameter? So the parameter of interest is the mean yield of the farms in the population. So which is y1, so which is the population mean, which is what? 1 plus 3 plus 5 plus 4, which is 6. Okay. So, so then 2 minus 6 is minus 4. So sampling error is nothing but the estimator minus parameter, right? So that is the error. So error, so 3 minus 6 equal to minus 3. This is 2 minus 2, 3, 4. Okay. So that is the error. So we have a 6 possible cases, right? So 6 possible cases, but in any case, we have an error. We have a error, either minus 4 or minus 3 or 2, minus 2, 3 or 4. Okay, so we cannot really avoid having errors, right? Usually, because we pay the price basically. Because we don't observe every element, but only observe a sample subset. So we pay the price. The price we pay is the error, the existence of error. Okay, so we are interested in selecting a sample that has a smallest error, something like that, right? But because we don't know the parameter, we don't know which one has a small, right? Smaller error. So then there's a 2 ways of selecting one of the 6 possible samples. So first one is, okay, maybe there's some information. The information we have is the size. So if I know, okay, since I know that maybe these two farms are in the middle, okay, in terms of size. So maybe I will just select the 2 in the middle and take the average. So which is actually 2 and 3 combination, right? So then that is a non-pair sampling. So use some information, select a sample subjectively. Okay. That is not really bad. I mean, it turns out that in this particular example, that's probably one of the best way, right? Smallest error, anyway. But here's a very intriguing idea. Okay, the idea is, okay, the idea is I can roll a dice. Okay, roll a dice and select one according to what the dice shows. So users basically randomly select. Okay, so because now I have a rule. So previously, right? Previously I just have 4 columns. So I have 4 columns, but now I have an additional column which assigns the probability rule. So then that is interesting because by assigning a rule, I basically have a way to select a sample, right? So that is sometimes called, so this pair is sometimes called the sampling design. How can I select a sample? But now let's take a look at this combination. So what it means? This one is more like a statistic, right? Y bar is a statistic, but this statistic has a probability now, and this statistic actually has a 6 possible values and with equal probability. That is nothing but just a discrete random variable, right? So y bar becomes a discrete random variable with a known probability distribution. So that is basically what we have. So this y bar, which is a random, is a statistic, becomes a random variable with known probability distribution. And then this one, now it becomes a mathematical statistical problem, right? So I can basically, because I know the probability rule, I can compute the expectation, for example. Okay. So then this one actually has the same 12. So 12 divided by 2, 6. Okay. But this 6 is what? Is actually population mean. Oh, what is going on? Huh. Let me see. Okay, let me share it again. Somehow it's not really yeah, so that is the problem with online delivery, right? You cannot really control something. Okay, so I recommend you to come the offline class as much as you can, because if something comes up, then I can just use no technology delivery. But here's today is too cold outside, so this is the best option we have. So anyway, right? This so interesting part is this statistic has known probability distribution. So that is sometimes called, basically this becomes a sampling distribution, right? Of y bar. So sampling design uh, somehow I think it has to do with my yeah. So should be right. Okay, it's going. So sampling design induces sampling distribution of random statistic, basically, right? Which is a function of yi in the sample. And furthermore, we can compute the variance, right? So basically, this is a sampling error. -4 square, -3 square, 2 square, -2 square, 2 square, 3 square, 4 square, something like that. So that you can, so that is basically 1/3, 16, 9, 4, 29 divided by 3, which is 6 or something. Okay. So by computing the variance, we can actually compare with other designs and make a decision, something like that. Okay. So that is the basically idea behind the probability sampling and what's going on with randomization. So if we reflect on this idea, what is going on behind this? So the magic here is that we basically assign probability, right? And that is a very interesting approach. And turns out that this is actually a totally different framework that we used to learn, right? We don't use any model, right? The only randomness comes from a selection, and which we assign. We know the design, so that is under our control. So no model assumptions about why in this example. So it is totally different framework, and it is design-based approach. So that means the reference distribution is the sampling distribution generated by the repeated application of the given sampling mechanism. So in some literature, this is they call it agnostic approach. Agnostic means we don't believe God, right? I mean, no God. So model is God. That means only God knows the true model. So agnostic means we don't rely on God, we don't rely on model to make an inference. So that is some literature they use agnostic approach instead of design-based approach. Okay. So here's some annotation. So U is a index set of finite population. So in survey sampling, we are mainly more interested in descriptive statistic and descriptive inference. So descriptive means mean, or right? I mean something that describes the population. So so then we have a very clear idea of the population, finite population, and then use so we'll use A to denote the index set of the sample, as script A is a set of samples on, so sample support, so all possible samples, and then set ahead is essentially a function of yi in the sample, so that is a statistic. Probability distribution of the sample is that so sample distribution or sample design, right? That basically is how we assign a priority to each possible sample. So for example, in this example, we just have equally, right? We distribute the all priority equally, so that is basically the priority rule. So we have in finite population, we have a finite sample support, right? So then the priority rule should be something satisfy these two, because it's basically priority mass function. Mass function. And then from the sampling design, we can induce, right? We can induce the priority distribution over statistic. So so then basically the randomness, so it is on A, on we could, because A changes, and we know the probability. So then this is basically the expectation, variance, and mean square error can be defined. Okay. So probability sampling basically means that we assign the probability, and the assignment should be in such a way that the probability that the element is included in the sample is known and greater than 0 for each element in the population. So we do not exclude any element in the population in terms of selection possibility. Okay, because otherwise we cannot really. So if a certain portion of the population is never selected, then how can we estimate the total, right? So that's impossible. So one of the minimum condition is that we should have a certain probability, even though it's a small. We should have a certain positive probability that every element in the population should be can be included in the sample. Okay. So this is especially popular in government statistics, because people may complain, or some politically, right? I mean, there's some political it's a sensitive, right? So then it could be, I mean, the numbers could be politically sensitive. So to achieve the best objectivity, then we probably impose certain randomness. So advantage is that we exclude the subjectivity of selecting samples, and then also remove the sampling bias or selection bias. So what is the bias, by the way? This is the error, right? The error can be decomposed in two parts. One is can be called the deviation. So the randomness from its mean, and then this guy is the mean of the infinite average of the random variable minus the parameter of interest. So in probability sampling, in non-probability sampling, so remember, suppose we just 1, 2, 3, 4, right? The two example. Suppose we just select 2 and 3, element 2 and 3, no matter what. Okay, suppose. Then there's no randomness, right? We just select 2 and 3 always. Then there's no variation. But there is bias, right? On the other hand, in probability sampling, there exists variation, but the bias is 0, right? Okay, so that is the advantages of probability sampling. So this one alone does not really tell you which one is better, right? It's possible that non-probability sampling could be more accurate than probability sampling in this, because so they have a different bias and variation. So bias square, what is the variation? Variation, average of variation square is a variance. So probability sampling, bias 0, variation is non-zero. Non-probability sampling, bias exists and variance is small. Variance is zero, essentially. Zero, zero. Okay. So this one doesn't really tell you which one is better. But nice thing about productive sampling is that we know how to control the variance in productive sampling. How? Increase the sample size, right? So if we increase the sample size, then variance gets smaller. But if in non-prime sampling, if we increase sample size, bias remains. So really, we cannot really control the bias with a large sample size. So there's an additional advantage. So that's why I call it additional advantage. So what is the additional advantage? Additional advantage comes from large sample. Okay. So if you increase the sample size, then you can get additional advantage in addition to what? To an original advantage. So this one is a genuine advantage regardless of sample size. So bias has nothing to do with the sample size. So even if the sample size is only one, you can still get unbiased estimator, right? So, and also you can get, exclude the subjectivity also, even with a small sample size. But to be useful, right? To be useful, and we need an additional thing. We need more, and which is basically achieved, which is achieved if we increase the sample size. Okay. So basically, two things. The first advantage is that additional advantage is that if we increase the sample size, we know that variance decrease, so that we can control the precision within certain level. And another thing is that for theory, statistical theory are well developed for probability sampling. Okay, so for the probability sampling, we have a theory such as law of large numbers or central limit theorem are developed for probability sampling, probability samples, not non-probability samples. Okay. In fact, for non-probability samples, law of large numbers doesn't hold. So that is the big problem, because yeah, because we want to. Well, actually, let me back up. Non-probability sampling. Well, this one may be okay for even for non-probability sampling. The problem is that this is not necessarily equal to zeta, right? For non-probability sampling. So bias exists. So even though we can say, so this is probably okay for any reasonable, any sampling. But this is not really interesting. What is interesting is whether this one holds, right? So this one is okay, is maybe okay for any what is let me, okay, so somehow, yeah, okay, so this is okay. The first statement is okay for any method, but it's not interesting, right? To us, or what we are interested in is we are interested in estimating zeta, not interested in estimating expectation of the zeta hat, right? So we are interested in zeta. So this is what we are interested in. This is the kind of our goal. And this goal is achieved. This goal is achieved for probability sampling only. Okay. Now, let's take a look at this second two example. So this is another probability sampling. Well, first question is this really, is it really a probability sample? Okay. So what is the definition of probability sampling, by the way? Let's go back. For here's a definition, right? For each element in the population, the probability that the element is included in the sample is known and greater than 0. Okay. So let's use this definition to check whether this design is a probability sampling design. So what is the probability of 1 in the sample? So the only way that unit 1 is in the sample is selecting this probability, right? 1, 1, 4 is selected. Because other combinations do not include unit 1. So this is the only way. And this probability is by design is 1/3. So this is known and positive. What about 2? Of course, this one is also 1/3, right? What about 3? Okay. And check. What about 4? This is interesting. 4, what is the probability of 4 is selected in the sample? Well, it turns out that if you look at this design, element 4 is always included, right? So that is actually 1. So this is positive and known. So this is indeed a probability sampling design, right? Because every element in the population has a known and positive probability of selection. Okay. So that means, so previous sampling design in example 1 here, right? This is actually some called simple random sampling. Simple random sampling means we give equal probability to every possible sample with a sample size, given sample size, right? So here the given sample size is 2. So among 4, selecting one of 2 out of 4, we have 6 possible combination. So that's why we get 1/6 probability to every possible combination. But this second example, right? This second sampling design is a different sampling design in the sense that in the 1, 2, 3, 4, basically we partition the population into 2 groups, right? And then unit 4 is always selected. That is somewhat makes sense because why? Because if you look at the original distribution here, unit 4, right? This guy is big farm. And so big farm, because it's big farm, the yield is likely to be high. Okay. So that means whether we include this farm into the sample or not creates a lot of variation. It's like a big company, right? I mean, suppose you are investigating some kind of total, what is the English? Total whatever product, commercial uh, product, and then a big company like Apple, right? If I select Apple by randomly, then whether I include the Apple company Apple into the sample or not creates a lot of a difference, right? So in that case, it's probably a good idea to choose big company in advance, okay, and then do randomness among small companies. So that's kind of an idea here. So basically, select with the property one. Okay, we already select it, and then select one with the property 1/3 equal property. So that is basically the sampling design. If I do that, then y value here. So this guy y represent. So this guy represents 3 farms, right? If I somehow choose one out of 3, then this value actually represent 3 farms, while this guy represents itself alone. So then the average is more like 3 times 1 plus 15 divided by 4. So which is 4.5. Here you can get this one, okay, to get this one. So the mean estimator, so selection property, we get this. So you can see, you can check that the expected value of a sampling, not sampling error, sample mean. So mean estimator, right? Expected value of mean estimator is 1/3 times 4.5 plus 6 plus 7.5, which is 6. Variance. What is the variance of y bar? Then 1/3 over 1.5 square, 0 square plus 1.5 square. So 2 times 2.25 divided by 3, right? So which is roughly 1 point something. Remember 4.5, 1.5 or something, right? Okay. So which is much smaller. So if you compare this number, this variance with 1.5, with this number, 9.66, right? Which one is smaller? This is much smaller than simple random sampling, right? Variance. Okay. That means what? That means this particular sampling design seems to be more efficient than doing simple random sampling. Okay. So survey procedure. This is outline of survey. So we need to define target population. We want to generalize. So from the sample, we should have a so finite population is a conceptual thing, but we target population should have a certain time, like for example, uh, uh, census, for example, if you census whoever lives in the United States in the year of April 1st in 2020 census. So should be confined in a time, and also the geography, right? So this is the population. Otherwise, if we don't allow this kind of restriction, then it becomes very vague. So there's a population to which the conclusions apply, and then what determine the population characteristic that we want to measure, and then find the sampling frame. Sampling frame is essentially a list that we want to assign probability. And then obtain a sample by a probability sampling design and measure the study variable and use measured values to compute the point estimates and standard errors. This is more like a procedure thing, planning and design and development, and implementation and evaluation. So key statistical component comes from this one, sampling frame, sampling design, and estimation. But because the whole thing is a kind of business, right? The actual operation, there's other things to consider. So these only maybe the imputation also is more like a data analysis. Okay, so these are the more statistical, but selection statement research question. What is the right research question and what is the questionnaire design? This is more like a domain specific. There's some domain knowledge, right? Like sociology or epidemiology. This kind of domain knowledge, domain interest should be involved. So this is more like a interdisciplinary operation. So survey, when it comes to survey design, there's two things. One is the sampling design, and the other one is questionnaire design. So this is actually, when it comes to survey sampling, when we say, okay, sorry, survey. This is actually two different concepts, right? Survey means measurement. Measurement, asking questions is about you have concepts, right? You have concepts. For example, employment, unemployment. So this is more like a domain specific concept that you want to ask, measure. And then to measure accurately, you need to develop some right question. You should ask right questions to get a good answer, right? So this is a questionnaire design, and sampling is more like a statistics, right? So so this is representativeness. So we want our sample to represent a finite population. So to obtain a representative sample, we need a proper sampling design, something like that. So, yeah. So let me use this. So there's two things. This is a survey. This is a sampling. Oh, yeah. Yeah, I think the internet in my house is kind of slow, so probably, or the weather. I don't know what is the real reason, but yeah. So measurement. One is the measurement aspect. The other one is a sampling aspect. So from the sampling, we want to do representation. We want to our sample should represent the population. A survey should should measure what we want correctly, right? Accurately. So this is a two to survey and statistic. And we as a statisticians care more about this the right side. The left side is not really our area. Actually, let me show you this. So this is actually survey statistics, right? So this is an area in statistics, and we are more interested in sampling errors. We want to measure the uncertainty of survey errors and incorporate them into estimation. And so this is more like a topics that we care about. Survey methodology is a more like a cognitive science. So that's a little bit different from our background, right? I mean, because we usually obtain measurement by asking questions. So how we can we ask right question, and or the terms should be clearly understood with each other, something like that. So by properly asking, so this is more like how to reduce survey errors, measurement errors, something like that. But that's a different area. Okay. So let me okay. So social errors. So there's a lot of errors, uh, uh, different type of errors, and sampling error is what we care about in 521. But other errors could be also is also common. What is the coverage error? So suppose we use so when it comes to assigned priority, we use list. But suppose my list is not really complete covers the population, then we have a coverage error. And non-response error is also a big problem in these days because people doesn't respond. Okay. So then how we kind of make up this non-response error is another important problem. And even we observe data, we have observation, we still could have errors like measurement error, right? Measurement error with the interviewer may ask improperly, or the could lie, or respondent could lie, or there's some kind of social desirability issue and all things like that. So a lot of different reasons for obtaining measurement with errors. Okay. So if any, so n is a sample size. Capital N is a population size. So if I select them all, right, select the population in the sample, every element in the sample, in the population into the sample, then of course, there's no sampling error. However, even if you n equal capital N, you may have a non-sampling errors. And the non-sampling error could be larger if we don't have a good training, good interviewers. So there's some skills that you get answers accurately, but if the interviewers are not really professional, then there could be some other issues. So because of the non-sampling error, a sample is often well designed. Well designed sample with well trained interviewers is often more accurate than a census. Okay. So I already covered this. So this course is about the sampling error and how to, particularly how to reduce it, right? And also how to measure it like a variance estimation. This one is more like design and also estimation. If you use a good estimator, you can do better, something like that. I think, yeah. Somehow, more. Yeah. You're almost done, but yeah. So this course is about the sampling error and how to reduce it and how to measure it. So that and to reduce it is more interesting, right? So by applying better sampling design or better estimation strategy, we can have a smaller variance. Okay, I think that's all for the first part of the lecture. Any questions? Okay, I got a chat. Okay. Any questions? Okay, I think this is all for today. And that's all for today. And we can talk. We can have a class next this Thursday at Snedeker Hall. Okay. Thank you. That's all.